300 million people can press play on Netflix, and every single one of them can pause on one device and pick that exact moment back up on another. Somebody had to design that, right? So welcome to Design Netflix. This is a 4-part series where we build Netflix backend the way a staff engineer would actually drive it in the system design interview. Today, episode 1, continue watching. After that, concurrent stream limits, then what really happens the instant you press play, and finally trending now, where we pull everything together into one giant diagram. By the end of today, you will walk away with the full architecture, the exact database schema, and the part most tutorials skip, the reasoning behind every design choice. Let's get into it. Here's the exact problem we are solving. You're on the couch, halfway through an episode on TV, and you pause. You get up, walk out, pull your phone out in the elevator, and it's right there. Resume to the second you left off. Feels effortless. It is generally hard to build. Because look at the scale, 300 million members, somewhere around a million playback events pouring every second. And here's the number that quietly decides this entire design. This system takes in roughly 9 writes for every 1 read, 9 to 1. Hold on that ratio. It's about to make almost every decision for us. Before we touch a single box or arrow, let's agree on how we attack this. Because in an interview, how you drive matters as much as what you draw. 5 phases. First, requirement. What are we actually building? Then scale estimate, where we put real numbers on it. Then the API and the data model. Then the high level design, the architecture itself. And finally deep dives and failure modes, which is honestly where most of the interview is won or lost. 2 rules keep us honest. Rule 1, one idea per phase. Don't jump ahead to storage while you are still planning down requirements. And rule 2, the big one, numbers before choices. We don't get to say the word like Cassandra until the math forces our hand. So let's start right there. Phase 1, requirements. Let's list what this thing has to do. And it's really just 3 things. 1, every device, your TV, your phone, your browser reports playback progress as you watch. It fires a start when you hit play, a heartbeat every so often while it runs, and it stops when you leave. 2, a member can ask where did I leave the title and get resume point back. So playback jumps straight there. And 3, they can pull up the whole continue watching row, that ordered strip of everything in progress. Now the non-functional requirements, and these are the ones that are actually shape the design. First, availability first. Eventual consistency is completely fine here. If your resume point is 2 seconds still on another screen, nobody notices. Second, it's heavily write heavy, that 9 to 1 again. Third, reads still have to be fast because this row blocks the home screen. So we target a P99 under 150 milliseconds. And fourth, it's global. You might pause in Dallas and resume in Delhi. Losing one heartbeat is fine, the next one corrects it. The only event we really need to protect is that the final stop. Okay, let's actually do the math. And the only math that changes the design. Start with 300 million members. Say each watches about 2 streams a day. While a stream plays, the client sends a heartbeat roughly every 30 seconds, plus a start and a stop. An hour of watching is about 120 of those events. Multiplied it all out, and you land nearly 72 billion events a day. Average that across the day, and it's around 800 to a million events every second. And on a big launch night, several times of that. And that one number makes 4 decisions for us before we have even named the technology. A single relational database as a primary, out. Nothing swallows a million writes a second in one box. So we need a store that's write optimized and stays available under load. We partition the data by member, so any one person's reads land in single place. And we put a queue in front, so those brutal bursts get absorbed instead of slamming the database. Still no product name. The shape came straight from the map. Let's design the right side first. How events get in. This part is deliberately boring, and that's the point. It's a plain REST endpoint, post to v1/playback events. The odd token writes in the header, not in the body. First, an event ID. A unique ID the client generates itself. Circle that one and it will matter in a minute. Then the title ID, which show the position in the millisecond, how far you are in next to the total runtime. So server can sanity check you are not somehow past the end. An event type, start, heartbeat or stop. And the client timestamps, when the event actually happens on the device, not when it arrives. And here's the single most important detail. The response is 202 accepted, not 200. 202 means I have received this, I have not processed it yet. That one status code decouples taking the event in from doing the work with it. And it's exactly what lets this endpoint absorb a million hits a second without the database ever being on a hard path. Back to that event ID. It's our idempotency key. Phones on a flaky network retry, so some events will arrive twice, and we need you using that idempotency key. And last, identity always comes from the token, a JWT token header, never in the body, because nobody gets to write into someone else's history. Now the read side, and the reads are totally different animal. So they go through Netflix GraphQL edge. Here's the query. We ask for continue watching the first 20 items. And this is the whole beauty of GraphQL. For each item we pull the title, its name, its art, the position, and the percent complete for drawing that little progress bar. The device asks for exactly what fields it needs. A TV wants a big artwork, a phone wants 3 fields, same endpoint, no custom routes per device. 2 things worth calling out for depth. Title here is a federated entity, that's the @key directive. Our continue watching service only owns the resume data. The catalog and artwork teams own their fields on the same title type, and the graph stitches them together. And when this row resolves 20 titles, we do not fire 20 separate artwork calls. Our data loader batches them into one. That's the classic n+1 problem, and we kill it right here at the edge. This is where the database earns its seat. So let's do it properly. 2 tables. The first, resume point, answers one question. Where did I leave this specific title? It's keyed on the profile ID and title. And the primary key means the lookup is single, pinpoint read on one partition. The second table, continue watching, is the row itself. Same profile partition, but notice this. We cluster by updated at descending order, which means the newest things you watch is already sorted at the top as it's written. So no sorting at read time. The table literally is the row. So why Cassandra? And the answer is never brand loyalty, it's its capabilities. 1. The write path is an LSM tree. Writes hit a log and memory. No read before write. Exactly what a million writes a second demands. 2. It's an AP store. In CAP terms, it stays available during a network partition and accepts eventual consistency. 3. It scales linearly. You grow by adding nodes. There's no single primary to outgrow. 4. Consistency is tunable. We read and write at local quorum, dialing latency against correctness per query. And 5. It fits this time series shape. Netflix even tiers it into live recent data and compressed history to keep partitions small. What did we turn down? Red is on its own. It's blazing fast, but this is a durable state, not a cache. And second, DynamoDB. Honestly a fine pick, same family. Cassandra is just the Netflix native answer with consistency knobs we want. Alright, let's put the whole thing on one screen and trace it end to end. It starts with clients, your devices. Every request first hits the edge gateway. At Netflix, that's Zool. It authenticates you, validates, rate limits, and under overload, it even shades heartbeats before anything important. On the right path, that playback event flows into the event ingesting service, which is stateless, validates, and fires back a 202. Then it produces the event into the Kafka, which is our queue. Why Kafka here specifically? Because it gives us ordering per member, it absorbs those launch night bursts, and it lets us replay history to rebuild state. And it fends one stream out to many consumers. Like this one, analytics, feeding recs and machine learning for free. The main consumer is Flink, the stream processor that folds all those raw events down into an actual resume point and the ordered row and writes them into Cassandra. Now the read path along the top. A device query hits the GraphQL edge, the federated router, which routes to the playback subgraph. Then the playback service wrapped in timeout circuit breakers. That reads through EVCache. It's a globally replicated, and only on the cache miss does it fall back to Cassandra. That's the entire system in one picture. Let's watch a single playback move through that pipeline, step by step, because the ordering is the whole story here. You press play, the client sends a start with a fresh event ID. The ingest service produces it to Kafka. keyed by your member ID, and instantly hands back a 202. It's a milliseconds here. The video just starts. Downstream, Flink consumes that event in order and upserts your resume point to 0. Now 30 seconds pass. A heartbeat fires. You are 31 minutes in, same path, reduce and fold. And your resume point quietly moves forward. That heartbeat cadence, by the way, is a dial. Fire every 10 seconds and the resume is fresher, but you triple the write load. 30 seconds is the sweet spot. Then later you stop 93% of the way through. That final event updates the row one last time. And because you are past 90%, the title drops out of continue watching and into the watch again. And notice the player never once waited on the database. Now the part that separates a design that works from one that's actually correct. Because networks lie. Story 1. You hit a stop at 48 minutes. The request goes out and times out. Did it land? The client has no idea. So it does the natural thing. It retries. With the exact same event ID, E9. And on the server, Flink sees it's already processed E9. So it just drops it. And it's no op. That's the idempotency rule. The key is minted once when the event is born and reused on every retry. If the client generated a fresh ID each attempt, delooping would be impossible. The story 2 is a little bit sneakier. Your phone was watching offline on a flight, buffering the events. Now it reconnects and flushes an old heartbeat, 45 minutes, with an old client timestamp. And Flink folds it in. But this would rewind you from the 48 back to 45. We block that. Two defenses do it. Last writer wins by the client timestamp. We trust when it happened, not when it arrived. Plus position monotonicity, which just means your resume point is never allowed to move backward within a session. So 2 deep dives left, and these are the ones that earn the senior title. First, global. Say you pause in the US and resume in India. Both regions run their own EVCache and Cassandra, replicated to each other. So wherever you are, that row reads locally in about a millisecond, a few seconds tail at worst. Reconciled by the same last writer wins rule, eventual globally, and the product generally does not care. Second, what if Kafka is unreachable? The collector fails fast with a 5xx, the client retries with a backoff, and the event ID means nothing is lost and nothing is doubled. What if Flink falls behind on a spike? The row goes down a little stale, playback is completely unaffected. A hot title stampedes the cache. Single flight locking plus a jitter TTL. One request rebuilds it, everyone else waits. And the real overload at the edge. Zool shades heartbeats first and protects start and stop last. We give up freshness to protect correctness. Every layer has an answer. So here is what you just designed. 4 patterns that travel way beyond Netflix. 1. Accept fast, process async. A 202 plus a partitioned log makes any ingest burst proof. 2. Client minted idempotency keys plus last writer wins keeps your data correct through retries and reordering. 3. Fold on write, so reads become one cheap single partition lookup. And 4. Choose an AP store on purpose, but only after you can say out loud why staleness is okay. In the next episode, we will flip the last rule completely on its head. Concurrent stream limits, where 5 people, 1 account, 4 streams plan. The one place eventual consistency is just wrong, and we build the atomic fix. If this made it click, drop a like and subscribe so you don't miss it. And tell me in the comments, would you have chosen eventual consistency here? Thanks for watching. Please like, share and subscribe, and I'll see you in the next one.